Welcome to another episode of the Flutter Build Show. I'm your host, Daco Harkes, a software engineer at Google in the Dart compiler and virtual machine team. In this episode, we're going to learn about build hooks and code assets, a new feature available in Dart 3.10. Some problems in computer science are either so annoying to solve or so performance sensitive that the whole world agrees to use a single blessed solution, almost always written in C. SQLite is just such a system, and while there are multiple SQLite packages on pub.dev, all of them use the same engine written in C. This means that Flutter developers using SQLite don't have to re-implement the engine, which is great. However, we do have to bundle a correctly compiled version of the SQLite engine into our apps in a place where our Dart code knows to look. Today, SQLite plugin authors solve that problem for us, but that hasn't been a fun experience. And that's where build hooks come in. They offer you a way to write simple Dart scripts that declare which non-Dart assets your app requires at runtime. And Flutter will move those assets in the right place every time you execute Flutter Run or Flutter Build. Let's take a look. To ensure everyone is on the same page, hooks are a software pattern by which systems allows developers to inject their own logic into its overall flow. In Flutter, we're adding build hooks for app developers to inject custom logic into Flutter's compilation steps to include non-Dart code dependencies called code assets. These new build hooks are conceptually simple. We'll write a few soon, but let's look at a high-level overview first. Build hooks are a Dart script which lives at hook/build.dart and which Flutter calls during compilation. Build hooks run in parallel to the rest of your compilation and receive a few necessary inputs like relevant directories and the target platform. In the end, the build hook produces code assets which Flutter includes in the app bundle for use at runtime by your app. Build hooks are proper Dart code, not YAML, so they can produce assets in a number of ways. For example, you can include system libraries, download a precompiled dynamic library, or even compile a code asset directly from source. And if compiling stuff directly from source sounds scary, fear not, for the Flutter tool is ready to help you with common scenarios. By default, Flutter caches the results of your build hooks, so it's not as if these files will be re-downloaded or recompiled every time you execute Flutter Run. But what about when, over the course of developing your app, you do need Flutter to rerun your build hooks? That's where the second build output comes in. Build hook should list all the files across your codebase that Flutter should include in its caching checksum. This means that whenever the contents of any of those files change, Flutter will no longer get a cache hit and will be forced to rerun your build hook. Note that Flutter always adds the build hook itself and any code it imports as dependencies, meaning you don't need to add them yourself. Packages from pub.dev can also include build hooks, so over time your Flutter app may depend and execute many build hooks while compiling your app. That's a high-level view of the actual hooks. But what about those assets? You might be wondering whether they're similar or related to the assets we declare in our pubspec.yaml files. They absolutely are. Assets in your pubspec.yaml file are data assets, while the files you produce in your build hook are called code assets. However, both get baked into your Flutter app bundle by the Flutter tool so that the Dart code knows where to find them. Just like data assets, code assets are discoverable by a unique ID. This is similar to how you also use a data assets path to, for example, display an image. We'll see where the code assets unique ID comes from later. Code assets have other attributes, but we'll see them in action as we work through 3 different examples that illustrate common use cases. First, we're going to link a system library, which is the simplest possible build hook you can write. Then we'll get more complicated by downloading a precompiled asset from the internet. And finally, we'll compile our own library and use all of the bells and whistles of Flutter's new build hook system. As we proceed, note that these full examples are available in the package code assets and linked in the show notes. Build hooks themselves are fully explained at dart.dev/tools/hooks. So, let's write our first build hook. This hook will add the ability to call the getHostName function, which exists in some form or another on every operating system. To start adding a build hook to your Flutter app or Dart package, add a few dependencies. Then create a new file at hook/build.dart and give it a main method. Next, call a special build function which comes from the hooks package. Build itself takes two arguments. First, it wants all the arguments that Flutter passed to this build hook. And second, it takes an asynchronous callback, which itself accepts two parameters, input and output. Right now, build hooks only support adding code assets, but that won't be true forever. So start by adding a check for which type of asset Flutter currently wants to build. Next, let's add a stop code asset to the output parameter. This will house all the information Flutter needs to correctly embed this resource into our app. The code assets constructor has three required parameters: package, name, and link mode. For package, supply the name of your Flutter app or Dart package. To avoid naming collisions, this must be the name in your pubspec.yaml. For name, supply a Dart library URI minus the leading package part. Together, the package and name define the asset ID. The formula to derive the asset ID is the word package, then a colon, then the value supplied to the package parameter, slash, and then the value supplied to the name parameter. You can supply anything you want for this name parameter, meaning the final asset ID does not actually need to be a valid Dart import. However, creating a valid import is less confusing later on. Since we're just calling a system API here, the function we need is already available. We just have to find it. For most of the possible platforms, the link mode we want is lookup in process, which means that at runtime, when we want to use the functions in this code asset, the Dart runtime will look up those functions in the running process. On Windows, we need to access the Windows system library instead of the Unix one. So now it's time to make use of that input variable to make sure we're setting up everything correctly for the target platform. The info we need is available at input.config.code.targetos, and we can switch on that to do something else for Windows. For Windows, ffigen will generate a different set of bindings. Additionally, the native function is lazily loaded from the system library, which comes standard on every Windows machine. This means we just have to include a reference to it. And lastly, throw an exception for any unexpected values. Our first build hook is complete. To review, this hook produces a simple code asset and doesn't have to declare any dependencies for the caching checksum, so it was pretty simple. This is all good and fun and all, but the whole point of this is that we can call the function from Dart, right? So let's do that. At this point, the code asset is baked into your Flutter app and is ready to use via Dart FFI. However, writing Dart FFI bindings by hand is tedious and error-prone, so we're going to generate the bindings with package ffigen from the system library headers instead. This video isn't an ffigen tutorial, so I'm going to breeze past the next part. Remember, all of this code is pulled directly from the examples in package code assets, and the full source is linked in the video description below, along with ffigen's own documentation. In a file at tool.ffigen.dart, add this boilerplate. Then establish your package root and create a generator. First, we need to specify what the generator should run on, the C headers. To create this unix.h file, I found the headers online. Then I made a new file at source/unix.h outside of the lib directory. And then I added the headers include statement that I found on the man page. After setting up the header configuration, we need to specify which C functions we're interested in, only get hostname. All the other functions are excluded by default to avoid generating a huge Dart file with thousands of bindings. Lastly, we need to specify the output where our Dart binding should be written. Now we're ready to call the generator's generate method. Next, our ffigen script also requires special handling for Windows. I'll copy-paste the FFI generator and update the header file and output file to Windows. Now, when you execute Dart tool/ffigen.dart, Dart will spit out a bunch of really fun-looking code, which exposes your fancy code asset to the rest of the application. We want to expose a more idiomatic Dart wrapper, so let's create a new file. Import the generated bindings and declare a function. Since we're calling native code, we have to worry about native memory, which includes freeing that memory to avoid memory leaks. To automate releasing memory, call the using function, which takes a callback that is past an arena object. That arena object can allocate memory, and when the using function completes, arena automatically releases any memory it allocated. Now we can allocate memory, call the correct platform's generated bindings, and return our value as a Dart string. Note that we want to give a nice Dart API here, so we'll have to convert the native string to a Dart string and convert any native errors to Dart exceptions. Let's write a test to see if our code works. We don't know, of course, what our hostname is, but at least it should not be empty or null. Let's run the test. It works! We just bound to native code, exposed the functionality in a nice Dart API, and at runtime the Dart code can access the system libraries via the code assets that we output in the build hook. Pretty neat! In the next example, things will get spicier by downloading a pre-built SQLite binary to include in our app. I'll create a new empty Dart package and add my dependencies, dev dependencies, and the hook/build.dart file. In that build file, I will add the same familiar starting code. The real code sample available in package code assets covers more edge cases than we have time to cover here, so for the purpose of the video, I'll focus on the highlights. First, I'll add a code asset to the output variable. Its package and name combine to produce an asset ID like before. And notice that link mode is simpler this time because all platforms will use the same type of resource, a downloaded file. Next, we'll need to actually download that file, so I'll create a helper function. What follows is a bit of pseudocode, but remember the full source is linked below. Because I'm currently on a Mac, I'll just handle that platform. On macOS, Homebrew is the easiest way to install SQLite, but that requires sudo. So I'll just see whether it's installed and warn the user if it's not. Finally, I'll return the file as a URI. For the full source code, check the links in the video description. The final step to actually call this code from Dart is to add ffigen. So I'll switch over to tools/ffigen.dart and add a declaration that looks pretty familiar. Note the SQLite header files value for the entry points. Just like with the headers for getHostname, it is our job to provide the headers. You can either automate this by downloading them in your build hook, or you can just pop over to the website and grab them manually and commit them in your Git repo. We've gone ahead and downloaded the headers from sqlite.org/downloaded.html and placed them in a third-party directory. Note that it's always a good idea to place any code in your package that is not under your own copyright in a third-party directory. For now, we're only interested in libversion just to see if we can use SQLite. And we'll pop the generated bindings into libsource third-party. Note that the generated binding should generally have the same copyright as the source of the bindings. Hence, we place it in a third-party directory. And you can pop the copyright in the output preamble. Now we run dart tools/ffigen.dart and we are able to import and call the generated bindings. Pretty neat. Okay, let's write a test to verify that everything works as expected. We don't know exactly what SQLite version we have, but we should definitely be 3 point something. Otherwise, we won't be able to work with it. Let's run the test. Sweet! What happened here in the background is that Flutter took the downloaded dynamic library and bundled it with the Dart code when it was run. Now that we know we can call native functions in the database engine, we could continue implementing calling functions to execute queries. But we'll leave that as an exercise for you. Or just head over to pub.dev and use one of the existing SQLite packages. We're on the home stretch now. All that remains is to compile SQLite from source. Interestingly enough, this scenario is actually the easiest of the three, thanks to the native toolchain C package. To start, you need the actual source. So I've placed SQLite.c from the same download page next to SQLite.h in my third-party directory. Now, in hook/build.dart, I can use the cbuilder library constructor from that native toolchain C package to compile the library. Note the map passed to the defines, which ensures native functions are visible in the Windows build. Once the builder object is ready, we call and await its run method. Notice how it takes the input and output parameters. It handles instantiating the code object for us. The C builder also includes SQLite C as a dependency, like so we don't have to. But if we weren't using a helper library, this is what it would look like to explicitly mark a dependency in our build hook. Ultimately, this means that if we ever update SQLite.c to a newer version, the build hook will be rerun. Inquisitive viewers may be wondering whether our previous ffigen specification for the downloaded SQLite package will change for the self-compiled version. And the answer is, it does not. The exact same ffigen Dart creates the exact same bindings which we can invoke in the exact same Dart code. Also, we can run the same test, but let's tweak it a bit. Since we have checked in the source code of SQLite, we know the exact version number. And the test passes. So that's build hooks and code assets. Other asset types are planned, but for now, this system enhances Flutter developers' ability to interface with industry-standard native libraries. This feature pairs well with Flutter's thread merge, which is what allows you to synchronously call system libraries like the one linked in the first example. For more info on that, check out the latest episode of Decoding Flutter titled The Great Thread Merge. And for everything else, head on to flutter.dev. Happy hacking!